Welcome. Understanding TLS like never before. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, I'm going to explain TLS 1.3, the security protocol that protects virtually every secure website you visit, in a way that anyone can understand. Imagine you're trying to have a private conversation with someone in a crowded room where everyone can hear you. That's essentially the challenge TLS solves on the internet. Every piece of data traveling between your browser and a website passes through dozens of computers and networks, any of which could be listening in. TLS creates a secure, private channel through all that noise. Think of TLS like setting up a secure phone line. When you first call someone, you need to verify you're talking to the right person, agree on a secret code for your conversation, and then use that code to scramble everything you say. But here's the brilliant part. TLS does all of this without ever speaking the secret code out loud. It's like two people creating a secret language while standing in Times Square, without anyone else being able to figure out what that language is. I will use real numbers, small ones you can follow along with, to show exactly how this works. Instead of talking about keys that are 256 bits long, that is a number with 78 digits, I will show you the same concepts using numbers like 7, 13, or 23. The math works exactly the same way, just with smaller numbers that we can actually understand and verify ourselves. We will see how your browser and a website perform an elaborate dance of messages, each one carefully designed to establish trust and create encryption keys without ever transmitting those keys. It is like a magic trick that happens billions of times a day, and today, you will understand exactly how the trick works. By the end of this presentation, you will be able to explain to anyone how secure internet connections really work. The secret handshake. Overview. Let me start with a simple analogy. Imagine you are at a masquerade ball and you need to identify and establish a secret communication channel with someone you have never met before. You are both wearing masks, like computers on the internet. There are eavesdroppers everywhere, like hackers. And you need to figure out a way to talk privately. This is exactly what happens every time you connect to a secure website. The TLS handshake is like a carefully choreographed dance with specific steps. First, your browser walks up to the server and says, "Hello. I speak these languages, which are encryption methods, and here are some random numbers I just made up." Why random numbers? Think of them as unique stamps that make this conversation different from every other. If someone records this conversation and tries to replay it later, these random numbers ensure it won't work, like trying to use yesterday's lottery numbers today. The server responds with its own hello. It agrees to communicate, stating, "Great, let us speak this language." During this, it selects one encryption method, provides its random numbers, and presents its ID card, which is a certificate, to prove it is really who it says it is. But the clever part is what happens next. Both parties need to agree on a secret key for encryption, but they cannot just say it out loud because everyone is listening. So they use a mathematical trick called Diffie-Hellman. It's like mixing paint colors. I can publicly show you yellow paint, you can publicly show me blue paint, and we both end up with the same green paint without ever showing the green to anyone else. Once they have this shared secret, the green paint, they use it to create multiple encryption keys, one for the browser sending data, one for the server sending data, and extras for verifying nothing was tampered with. The entire process takes about 100 milliseconds faster than a blink of an eye. In that time, the two computers have verified each other's identity, created unique encryption keys that exist nowhere else in the universe, and established a secure channel that would take all the world's computers millions of years to crack. And they did it all while everyone was watching, without ever revealing their secrets. Client says hello. Let's dive deep into the very first message. The client hello. Imagine you are walking into a bank for the first time. You do not just walk up to the vault. Instead, You first go to the receptionist and introduce yourself. The client hello is exactly that introduction, but it is packed with crucial information that sets up everything that follows. First, your browser generates 32 bytes of random data. Now, what's a byte? Think of it like a single character in a text message. So 32 bytes is like a 32-character password. But here's the key. It must be truly random. Not pick a number between 1 and 100 random, but roll a million dice and use quantum physics random. Why? Because if an attacker can predict this number, they might be able to break the encryption. Your computer usually gets this randomness from things like the exact microsecond timing of your mouse movements, keyboard presses, and electrical noise in the circuits. Next, the browser lists the encryption methods it knows, like I can speak AES with 128-bit keys, AES with 256-bit keys, or Cha-Cha 20. Think of these like different languages. AES is like English, widely spoken and well understood. Cha-Cha 20 is like Spanish, equally good but optimized for different situations, mobile devices in this case. The browser lists these in order of preference, like saying I prefer English, but I also speak Spanish and French. But here's the revolutionary part of TLS 1.3. The browser also sends key shares. In older versions, establishing a shared secret took multiple back and forth messages. It was like saying, do you want to create a secret? Yes. Okay. Here's my part. Here's mine. TLS 1.3 shortcuts this by having the browser say, here's my part of several possible secrets. Pick whichever one you like. It's like showing up to the bank with several different forms of ID, knowing they'll accept at least one. For the key shares, let me use small numbers. The browser might say, for group 23, my public number is 4. In reality, these are huge numbers. The browser calculated this by picking a secret number, say 3, and calculating 2 to the power of 3 modulo 23 equals 8. But I said 4 to keep it simple. The important part is that the browser sends the result, 4, but keeps the process, 3, secret. It's like showing someone a locked box but keeping the key. Server responds. Now, we come to the server's response. The server hello. If the client hello was like walking into a bank and introducing yourself, the server hello is like the bank manager coming out, shaking your hand, and saying, welcome. Let me show you my credentials and let's set up your secure account. But so much happens in this one message that it is worth examining every detail. First, the server makes some decisions. It looks at the client's list of encryption methods and picks one they both support. It is like the client said, I speak English, Spanish, and French, and the server responds, great, let us speak Spanish. This choice is final. There is no negotiation. The server typically picks the strongest option that both sides support, like choosing a deadbolt over a simple lock when both are available. The server also generates its own 32 bytes of random data. Remember how the client had random data too? When you combine both random values, you get 64 bytes of randomness that's unique to this exact conversation. It's like both people contributing half of a lottery ticket number. Neither party can control the final number, and it's astronomically unlikely to ever repeat. In cryptography, this is called contributory behavior. Both parties contribute to the randomness to ensure neither can manipulate it. Here is where the magic happens. The server looks at the key shares the client sent. Let's continue our small number example. The client said, for group 23, my public number is 4. The server now picks its own secret number, say 5, and calculates 2 to the power of 5 modulo 23 equals 9. The server sends back 9 as its public number. Now watch this. The server takes the client's public number, 4, and raises it to its secret power. 4 to the power of 5 modulo 23 equals 13. Meanwhile, the client will take the server's public number, 9, and raise it to its secret power. 9 to the power of 3 modulo 23 equals 13. They both get 13 without ever sharing their secret numbers. Immediately after sending the server hello, something crucial happens. The server switches to encrypted mode. It uses that shared secret, 13 in our example, to derive encryption keys, and everything else it sends is encrypted. This is new in TLS 1.3. In older versions, much more of the handshake was sent in plain text. It is like switching from talking openly to whispering in code mid-sentence, and only the client can understand the code because they have the same shared secret. The math magic. Creating shared secrets. Let me pull back the curtain on the mathematical magic that makes TLS work. This is the Diffie-Hellman key exchange, and I'll explain it using simple numbers you can verify with a calculator. This is the same math that protects billions of dollars in online banking, just with smaller numbers so we can understand it. Let's use a complete example. We'll work with a prime number 23 and a generator 5. Think of these as the rules of the game that everyone knows. The client, let's call her Alice, picks a secret number 6. She calculates 5 to the power of 6 modulo 23. Now, 5 to the power of 6 is divide by 23, and the remainder is 8. So Alice sends 8 to the server, Bob. Meanwhile, Bob picks his secret number 15 and calculates 5 to the power of 15 modulo 23, which equals 19. He sends 19 to Alice. Here's where it gets magical. Alice takes Bob's public number, 19, and raises it to her secret power, 19 raised to the power of 6 modulo 23. Bob takes Alice's public number, 8, and raises it to his secret power, 8 raised to the power of 15 modulo 23. Incredibly, both calculations give the same answer, 2. They have created a shared secret, the number 2, without ever transmitting it. An eavesdropper who sees 8 and 19 cannot figure out the secret without solving the discrete logarithm problem. This essentially involves running the calculation backwards, which is practically impossible with large numbers. In real TLS, instead of 23, we use prime numbers that are hundreds of digits long. Instead of secrets like 6 or 15, we use numbers with 77 digits. The public numbers exchanged would have 77 digits too. But the principle is exactly the same. It would take all the computers on Earth working together for longer than the age of the universe to work backwards from those public numbers to find the secrets. But wait, there is more. TLS 1.3 does not just use this shared secret directly. That would be like using the same password everywhere. Instead, it feeds this secret through a key derivation function. Imagine a machine that takes one secret and produces multiple different keys from it. It is like having a master key that you put into a special machine, and out come separate keys for your house, car, office, and safe. Each key is different, but they all came from that one master secret. This way, even if someone somehow steals your car key, they cannot get into your house. Encrypted messages begin. Once the server hello is sent, something remarkable happens. The entire nature of the conversation changes. It is like two people who were talking normally suddenly switch to speaking in code, and the code is so complex that even supercomputers cannot break it. Let me explain exactly what gets encrypted and why this matters so much for your privacy. The first encrypted message is called encrypted extensions. Think of this like whispering additional details that you don't want others to overhear. In the clear part of the handshake, the client said, "I want to connect to example.com." But now the server can privately confirm, "Yes, I am example.com, and by the way, we'll use HTTP/2 for faster loading, and I support uploading files up to 10 megabytes. All these details are now hidden from anyone watching the connection. Why hide these details? Imagine you're connecting to a server that hosts multiple websites. Without encryption, anyone watching can see exactly which site you're visiting. With TLS 1.3 encrypting these extensions, observers can only see that you're connecting to the server, not which specific service you're using. It's like seeing someone enter an office building but not knowing which office they're visiting. The encryption itself uses the keys derived from our shared secret. Remember our example where Alice and Bob created shared secret 2? That goes through a process like this. Take the shared secret 2, mix it with the transcript of all messages so far. Imagine a summary of the conversation. Add a label like client handshake traffic, and run it through a special function that outputs a much longer key. For example, 16 bytes for AES 128. It's like putting ingredients in a blender where even a tiny change in inputs creates a completely different smoothie. Here is what makes this encryption unbreakable. For AES 128, there are a total of 340 undecillion possible keys. If you tried one key every nanosecond, it would take billions of times longer than the universe has existed to try them all. And remember, this key is unique to this exact conversation. It has never been used before and will never be used again. Every single TLS connection creates its own unique keys that exist for just that conversation and then disappear forever. Proving identity. The certificate. Now we come to a crucial part. How does the server prove it's really who it claims to be? This is where certificates come in, and I'll explain them using a real-world analogy everyone can understand. Imagine you're buying a house. You don't just trust that the seller owns it. You check with the government land registry. TLS certificates work the same way, but for websites. A certificate is like a driver's license for websites. Just as your license has your photo, name, and address, a certificate contains the website's name, for example, www.example.com. It also contains its public key, and remember, that's the number it uses for the Diffie-Hellman exchange, along with an expiration date. But here's the key part. Just like your license has an official government seal that's hard to forge, the certificate has a digital signature from a certificate authority, or CA. Certificate authorities are like the DMV of the Internet. There are only a few dozen trusted ones worldwide. Companies like DigiCert, Let's Encrypt, and GlobalSign. Your browser comes pre-installed with their public keys, like having a book of official government seals to verify licenses. When Amazon wants a certificate, they must prove to a CA that they really own Amazon.com. The CA then signs a certificate saying, yes, this public key really belongs to Amazon.com. Let me show you with simple numbers how the signature works. Let's say the CA's private key is 7 and public key is 13. The certificate contains information such as site equal Amazon.com, public key equals, expires equal December 2024. The CA calculates a hash, like a fingerprint, of this information. Let's say it equals 29. The CA then signs by calculating 29 to the power of 7 mod 33 equals 17. Anyone can verify this signature using the CA's public key. 17 to the power of 13 mod 33 equals 29, matching the original hash. In TLS 1.3, this certificate is sent encrypted, which is new. In older versions, anyone could see which certificate was being sent. Now it is private, like showing your ID inside a private room instead of in public. The server actually sends a chain of certificates, its own, plus intermediate certificates leading up to a root CA your browser trusts. It is like showing your driver's license, plus the letter from the DMV confirming it is real, plus documentation that the DMV is officially recognized by the government. The digital signature. Certificate verify. Having a certificate is like having a passport. It identifies you, but you still need to prove you are the person in that passport. That is what the certificate verify message does. It is the server proving it actually owns the private key that matches the public key in the certificate. Let me explain this with an analogy that makes it crystal clear. Imagine the certificate is like a house deed that says John owns this house, and here's a photo of the unique front door key. But how do we know the person claiming to be John actually has that key? It's simple. We ask them to unlock the door. The certificate verify is exactly that. It's the server using its private key to create a signature that only the real key holder could create. Here's what makes this signature special. It's not just signing anything. it's signing a summary of the entire conversation so far. It's like John not only unlocking the door but also reciting everything that's been said in the conversation to prove he's been present the whole time. This prevents replay attacks where someone might try to reuse an old signature. Let me show you with simple numbers. The server has private key 11, kept secret, and public key 7 in the certificate. The conversation transcript might hash to 15. The server creates a special message. I am the server for this exact TLS 1.3 conversation with hash 15. It then signs it, calculating 15 to the power of 11 modulo 23, which results in 19. The server sends 19. The client, using the public key from the certificate, calculates 19 to the power of 7 modulo 23, which equals 15. Since this matches the transcript hash, the client knows the server has the private key. In reality, this signature uses RSA with 2048-bit keys or elliptic curves. The numbers are so large that creating a fake signature would require factoring numbers with 600-plus digits, which would take all the world's computers millions of years. It's not just hard, it's mathematically impossible with current technology. This is the only time in the entire TLS 1.3 handshake where the server's long-term private key is used, and it's only used for proving identity, never for encryption. This design means even if someone records all your encrypted traffic and later steals the server's private key, they still can't decrypt your past conversations. Handshake complete. The finished messages. We have reached the grand finale of the TLS handshake, which are the finished messages. Think of these as both parties signing a contract, but instead of signatures, they are using cryptographic proofs that verify everything that has happened. It is like ending a phone conversation by both people reciting a summary of everything discussed, to confirm they heard the same things. The finished message is beautifully simple, yet powerfully secure. Each party takes the entire transcript of the handshake, every single byte that has been sent or received, and creates a cryptographic hash of it. A hash is like a fingerprint. Change even one bit in the messages, and the hash completely changes. Then they use their traffic keys to create a MAC, message authentication code, of this hash. It's like taking a photo of all the documents, and then putting them in a tamper-evident envelope. Let me use simple numbers to illustrate. Let's say the handshake transcript, which includes all messages, when fed through a hash function, produces 42. The server uses its server handshake traffic secret, let's say it's 17, and computes HMAC, with 17 and 42, which equals 88. This 88 is the server's finished message. When the client receives this, it computes the same thing. It has the same transcript, which means the same hash of 42, and it derived the same secret, 17. So, it also gets 88. If they match, the client knows the server received all messages correctly. The client then sends its own finished message using the client handshake traffic secret. Here is the significant aspect. Once both finished messages are verified, both parties have mathematical proof that 1. They both derived the same keys from the Diffie-Hellman exchange. 2. They both received all messages without tampering. 3. They are both ready to start encrypting application data. And 4. No attacker interfered with the handshake. Immediately after sending its finished message, the client switches to the final application keys. The server does the same after receiving the client's finished. These application keys are different from the handshake keys. It's like changing the locks after construction workers finish building your house. From this point on, all your actual data, web pages, form submissions, videos, is encrypted with these application keys. The handshake is complete, and you have a secure channel that would take longer than the age of the universe to crack. Your data flows securely. Now that the handshake is complete, the real purpose of TLS begins. Protecting your actual data. Every search query, every password, every credit card number you type is now protected by the keys established during the handshake. Let me show you exactly how your data is encrypted and why it is so secure. Remember our shared secret and all those keys we derived? Now they are put to work. When you type "what is the weather" into a search box, your browser does not just encrypt those letters. First, it adds what is called a sequence number. For example, imagine numbering each message like this is message number 1, this is message number 2. This prevents an attacker from reordering or replaying your messages. It is like numbering pages in an important document so no one can shuffle them. Next, the browser encrypts using AES or SHA-20. Let's consider some simple numbers. If your message is 37 and the key is 19, the encrypted result might be 84. But here is what is clever. Even if you send the same message twice, it encrypts differently each time because of the sequence numbers. Sending "hello" twice might give you encrypted values of 84 and 52. An attacker seeing 84 and 52 has no idea they are both "hello." But encryption alone is not enough. TLS also adds an authentication tag. Think of it like a wax seal on an envelope. This tag is calculated from the encrypted data and can only be created if you have the key. If anyone changes even one bit of the encrypted message, the tag will not match when the server checks it. It is like having a seal that shatters if anyone tampers with the envelope. The numbers involved are staggering. Every second, your connection might encrypt hundreds of messages. Each uses a unique combination of key and sequence number, creating encryption that's never been used before and will never be used again. Over the lifetime of your connection, you might use millions of different encryption combinations, all derived from that initial handshake. And here's the beautiful part. All of this happens so fast you don't even notice. That little padlock in your browser represents one of the most sophisticated cryptographic protocols ever designed, working tirelessly to keep your data safe. From the initial hello to the final goodbye, TLS 1.3 ensures that your private conversations stay private, using math that would take the world's fastest supercomputers millions of years to break. Session resumption. The returning customer fast lane. Imagine you're a regular at your favorite coffee shop. The first time you visited, you had to show ID, fill out a loyalty card application, and establish your preferences. But now when you walk in, the barista recognizes you and says, "The usual?" That's exactly what session resumption in TLS 1.3 does for secure connections. When you first connect to a website, after completing the full handshake we discussed, the server can give you a session ticket. Think of this like a VIP membership card. The ticket is actually encrypted data that only the server can read, containing information about your previous connection. It's like the coffee shop giving you a card with your encrypted order preferences that only their system can decode. The magic happens when you return to the website, maybe minutes or even days later. Instead of going through the full handshake again, which took 100 milliseconds, your browser includes this session ticket in the client hello. It is like flashing your VIP card at the door. The server decrypts the ticket, sees "oh, I remember this client," and can immediately establish encryption using information from your previous visit. Let me explain with simple numbers. In your first visit, you and the server created a shared secret, let's say 42. Before you left, the server created a ticket containing secret equals 42, created equals Monday, cipher equals AES. It then encrypted this ticket with the server's special ticket key, which only the server knows. The encrypted ticket would be a jumbled string of characters. The server gives this to your browser, which stores it, much like keeping a receipt. When you return, your browser sends this ticket. The server decrypts it, sees the shared secret was 42, and can immediately derive new session keys from it. Instead of all the certificate checking and Diffie-Hellman calculations, you skip straight to secure communication. It's like the difference between a 10-minute coffee shop visit for a new customer versus a 30-second transaction for a regular. The time savings are huge. We go from 100 milliseconds to about 0 to 50 milliseconds, making websites load noticeably faster. 0 RTT. Speaking before the handshake completes. Now we come to one of TLS 1.3's most innovative features. 0 RTT, or Zero Round Trip Time Resumption. This is like being such a regular customer that you can shout your order while walking through the door, before even reaching the counter. It sounds impossible. How can you send encrypted data before establishing a connection? Let me explain this cryptographic magic trick. Remember the session ticket from our last slide? Well, TLS 1.3 takes it one step further. When the server gives you that ticket, it's not just for faster reconnection. It also includes enough information to start encrypting immediately on your next visit. It's like the coffee shop giving you a special app where you can place your encrypted order before you even arrive at the shop. Here's how it works with simple numbers. During your first visit, you establish shared secret 42. The server's ticket includes this information. When you return, your browser can immediately derive an early traffic secret from this saved information. Let's say it calculates early key equals 17. Without waiting for any response from the server, your browser can start sending encrypted data using key 17. It's literally 0 round trips, hence the name. But there's a catch, and it's important. This 0 RTT data can be replayed by an attacker. Imagine someone recording you shouting one large coffee as you enter the shop. They could replay that recording and you'd end up with 2 coffees. Similarly, if you send transfer $100 as 0 RTT data, an attacker could replay it. This is why 0 RTT is only safe for idempotent operations. These are things that are safe to repeat, like loading a web page or checking your balance. The browser might send the request get/index.html encrypted with the early key. The server decrypts the ticket, derives the same early key, and can immediately decrypt and process this request. By the time the handshake completes, your web page is already loading. It is like your coffee being ready before you reach the counter. Websites can load 30 to 50% faster with 0 RTT, but developers must carefully choose what data can be sent this way. It is a powerful feature that trades a small security consideration for a massive performance boost. Client certificates. When you need to show ID too. So far, we've focused on the server proving its identity to you, like a bank showing you their official charter. But sometimes, the server needs to verify who you are too. This is where client certificates come in. It's like entering a high-security building where you don't just verify the building as legitimate. They also need to verify you have clearance to enter. Client certificates are commonly used in corporate environments, online banking in some countries, and government websites. Instead of just using a password, something you know, you also prove who you are with a certificate, something you have. It's two-factor authentication built right into TLS. Think of it like having a special ID card that's impossible to forge, stored securely on your computer or on a smart card. The process works like this. After the server sends its certificate, it can send a certificate request message. This is like the security guard saying, "I have shown you my badge, now please show me yours." The request specifies what types of certificates are acceptable. For example, perhaps only certificates issued by your company's internal certificate authority. It is like saying, "I only accept ID cards issued by this specific agency." Your browser then sends its own certificate message, followed by certificate verify. Just like the server did, you are proving you own the private key matching the certificate. Using our simple numbers, your certificate contains your public key 11, and you have private key 7. You sign the handshake transcript, hash equals 23, by calculating 23 to the power of 7 mod 33 equals 14. The server verifies this with your public key, 14 to the power of 11 mod 33 equals 23. Perfect match. What makes client certificates so secure is that they are nearly impossible to steal remotely. Unlike a password that could be phished or guessed, the private key never leaves your device. Even if someone watches all your network traffic, they cannot extract your private key. It is like the difference between someone overhearing your password versus trying to steal a physical key from your pocket. This is much harder. Many high-security organizations require client certificates because they provide the strongest form of authentication available in TLS. Post-handshake authentication. Checking ID mid-conversation. Here's a unique feature of TLS 1.3. The ability to request client authentication after the handshake is complete. It's like having a normal conversation with someone, then halfway through saying, "Actually, before we discuss this sensitive topic, I need to see your ID." This wasn't possible in older TLS versions. Authentication had to happen during the initial handshake or not at all. Why is this useful? Imagine visiting a website where most content is public, but certain sections require authentication. In the past, you would need separate connections or complex workarounds. With post-handshake authentication, you can browse freely. Then when you click Access Account, the server can request your certificate without restarting the connection. It is like walking freely through a museum, but needing to show special credentials only when entering the VIP exhibit. The process is elegantly simple. At any point after the handshake, the server sends a certificate request message. But here's the clever part. This happens over the already encrypted channel using the established application keys. It's like passing a note that says "Please show ID" in an envelope that only you can open. The privacy is maintained throughout. Your browser responds with certificate and certificate verify messages, just like in the handshake, but now encrypted with the application traffic keys. Using our example numbers, the current application key might be 29. All messages are encrypted with this. The server requests authentication. You sign the current transcript hash, say 45, with your private key. 45 to the power of 7 modulo 33 equals 12. This signature, along with your certificate, is encrypted with key 29 before sending. This feature enables sophisticated authentication flows. A website could allow anonymous browsing, request certificates for medium security areas, and require additional authentication methods for high security operations. It's like a building where the lobby is open to all. Offices require an ID badge, and the vault requires both badge and biometric scan. All of this happens over the same TLS connection, maintaining efficiency while providing flexible security exactly where needed. Hello retry request. When the server says try again. Sometimes the first client hello isn't quite right, like ordering at a restaurant in a language the waiter doesn't understand. The server needs something different from what the client offered. This is where hello retry request comes in. It's the server's way of saying, "I'd like to establish a connection with you, but I need you to offer different options." This might sound like a step backward, but it's actually a clever optimization. The most common scenario is with key shares. Remember how the client sends public keys for different groups. If a client sends key shares for P256 and X25519, but the server only accepts P384 for regulatory reasons, it cannot proceed. In TLS 1.2, this would mean connection failure. In TLS 1.3, the server sends hello retry request saying, "Please send me a P384 key share instead." Here's how it works with our simple numbers. The client initially offers, for group 23, my public key is 8, and for group 47, my public key is 15. The server needs group 97 for compliance reasons. It sends a hello retry request, stating, "I need group 97 instead." The client generates a new key pair for group 97 with a private key of 6 and a public key of 34, and sends a new client hello with this key share. Now the handshake can proceed normally. What's brilliant about this design is that it's not really starting over. The client includes a hash of the original client hello in the new one, cryptographically binding them together. It's like saying, "Here's my new order, and here's proof that this is a continuation of our previous conversation, not a new one." This prevents an attacker from manipulating the retry process. Hello retry request also enables cookie challenges to prevent denial of service attacks. If a server is under attack, it can respond with hello retry request containing a cookie, like a CAPTCHA for TLS. The client must echo this cookie in its retry, proving it received the server's message. It is like a bouncer asking you to repeat a phrase to prove you are not just a recording. This simple mechanism helps servers stay online during attacks, while legitimate clients experience only a slight delay. This might add perhaps 50 milliseconds to establish a connection that is then secure for hours. What happens when you click a link? Let's trace the complete journey of what happens from the moment you click an HTTPS link to when the page appears on your screen. This real-world walkthrough will show you how all the TLS pieces we've discussed work together in the fraction of a second it takes to load a secure web page. It's a symphony of cryptography happening faster than you can blink. The journey begins when you click a link to https://shop.example.com. Your browser first needs to find the server's address, DNS lookup, then establishes a TCP connection, like dialing a phone number and waiting for it to ring. This takes about 10 to 30 milliseconds. Now the TLS handshake begins. Your browser prepares the client hello with random numbers, supported ciphers, and key shares. If you have visited before, it includes a session ticket. Let's say this is your first visit. Your browser generates ephemeral keys, perhaps private key 7 for X25519, then calculates public key 21. The client hello flies across the internet to shop.example.com server. The server, running powerful hardware, processes thousands of these per second. It chooses AES-128 GCM, generates its own ephemeral key pair, private 13, public 39, and computes the shared secret, 21 to the power of 13 mod group size. Within 5 milliseconds of receiving client hello, the server sends back server hello with its public key, then immediately switches to encryption. The certificate verify, and finished messages are already encrypted. Your browser receives these, verifies the certificate against its trusted roots, checking is this really shop.example.com, confirms the signature, and sends its own finished. Total time: about 50 to 100 milliseconds depending on your distance from the server. Now, for the magic moment. Your browser sends get/product/widget.html encrypted with the application keys. The server decrypts this, fetches the web page from its database, compresses it, encrypts the response, and sends it back. Your browser decrypts the data, decompresses it, and renders the HTML images, CSS, and JavaScript files flow through the same encrypted channel. From click to fully loaded page, typically 200 to 500 milliseconds. In that half second, your browser and the server performed hundreds of cryptographic operations, verified identities, and established a secure channel that would take adversaries millions of years to break. And you just saw a web page appear. How your password stays safe. One of the most critical uses of TLS is protecting your passwords as they travel from your browser to a website. Let me take you inside this process to show you exactly how TLS keeps your credentials safe from the millions of potential eavesdroppers between you and the server. This is why that little padlock icon in your browser is so important. For example, let's say your password is mysecret123. When you type it into a login form, it exists in plaintext in your browser's memory. Without TLS, when you click login, this password would travel across the internet exactly as you typed it. Anyone monitoring the network, your ISP, coffee shop Wi-Fi operator, government agencies, hackers, could see mysecret123 flying by. It's like shouting your password in a crowded room. With TLS, here is what happens instead. Your password becomes part of an HTTP POST request. Username equal operator Alice and sign password equal operator mysecret123. This entire message is encrypted using your session's application key. If your key is 73 and using AES encryption, my secret 123 might become. But it is not just encrypted once. The entire HTTP request, including headers, cookies, and your password, is wrapped in TLS encryption. Let me trace the journey with simple numbers. Your password MySecret123 is first combined with other form data. This creates a message that is, for example, 100 bytes long. Your browser adds padding to hide the exact length, so attackers cannot guess password length, making it 128 bytes. It generates a unique nonce from the session IV and sequence number. Then it encrypts. AES, with key equal to 73, nonce equal to sequence 5, and data equal to your password plus form. The output is completely random looking. But TLS goes further. It adds an authentication tag to ensure nobody tampered with the data. It's like putting your password in a locked box for encryption, and then sealing it with tamper-evident tape for authentication. If anyone tries to modify even one bit of the encrypted password, the authentication tag won't match when the server checks it. The server will reject the entire message rather than risk processing tampered data. This multi-layer protection ensures that your password remains confidential and unmodified from the moment you click login until the server receives it, no matter how many networks it crosses or who might be watching.